Now, when it comes to special cases, we can use the same example that we used yesterday. It's slightly different in the textbook, but don't worry about it. It works in exactly the same. I will also deal with the examples given in the textbook. So, there is a force F that acts in that direction. This is a pulling force. I can put it exactly on the other side also. It means exactly the same. And this causes a certain displacement in the object. It's going to overlap a bit. I hope you don't get confused. While the force is being applied, okay, and there is a displacement S that is being caused as a result of this. Now, when you apply this equation, you can write it down like this. First of all, identify theta. Okay, so theta is in this case, it is the angle between the direction of displacement and the force being applied. It's a very good idea in these cases to actually write down your axis system. Okay, so you write down the Cartesian coordinate system, x-axis, y-axis. I'm just putting the positive parts because I'm just using it for reference. So in what direction is force acting? Along the positive direction of S. In what direction is the displacement? Along the positive direction of S. Since these two are parallel to each other, the value of theta therefore is 0 degrees. Okay, so now you can write down the value as W is equal to F times S times cos 0 degrees. Okay, and a quick examination at the scientific calculator, or you can Google it, will tell you, of course, that cos theta has a value of 1. So work becomes F times S times 1. So then in this case, you simply get F times S. So this is your first equation. Okay, so this is how you got the first equation. That is a special case when the theta is equal to 0 degrees. That means the force and the displacement are in the same direction. Now let's take the second case. Okay, so this is the second case. I'm just drawing a line here to delineate the two. I'll draw it a little bit higher and a little bit smaller. And in this case, the force is being applied in this direction. Okay, that is perpendicular, horizontal direction. Okay, horizontal to the plane on which the object lies. So the required displacement that we are looking at is in this direction, is along this direction. Okay, but obviously there is going to be no displacement that will take place in that direction. So now we can say that theta, which is the angle between the force and the required distance, the required direction of displacement. And again, using the coordinate system, we can see that they are at right angles to one another. It's obvious even in the diagram, but just for reference. So you say that now theta is equal to 90 degrees. Now to calculate work done, again apply the equation F times S times cos theta. Of course, the way I am writing out is the way you are expected to answer questions in the board. Okay, so those of you who are in the habit of writing down notes, if you are writing this down, just mark it out as expected format of writing examination answers. Okay, so they want you to write down the equation, they want you to write down the variables, and then they want you to do the calculation and finally give an answer. This is of course more like a derivation than actually a problem solving, but I'm just saying that the format is more or less the same. So then you can write this as F times S times cos 90 degrees, and again looking at the calculator, the Clark's table, or just knowing it from memory, you should know that cos of 90 degrees is equal to 0. So you get F times S times 0. So that work done is equal to 0 Newton meter. Okay, so interestingly here you get an equation. In this case you get an equation F times S. Why? Because it has not been specified. F and S have not been specified, but if it is specified, then you can calculate. But in this case, you get a specific answer, which means it does not matter what the force and the displacement are that are being given to you. One or the other will be given, obviously. The answer will always be 0. So you don't even need to calculate in this case. If the two quantities are at right angles to one another, then no work is done on the object in the direction of the applied force. So these two are the special situations that are part of your syllabus. Now I will talk about one more special situation which is not part of the syllabus. I don't think it is mentioned in the syllabus document, and also neither has it been asked as a question as far as I can remember in the last few years. So the type of question that you can be asked is, why is it that when a force is applied at right angles to the direction of motion of an object, that no work is done? So you may be required to argue this, that cos 90 degrees work is equal to Fs cos theta. Since theta is equal to 90 degrees, cos theta is equal to 0, therefore no work is done. You may be required to write something like that. If it is just a 1 mark answer, you just write cos 90 degrees is equal to 0, W is equal to F times S times 0, and finish it off. If it is for a 2 marks or 3 marks, 3 marks is highly unlikely. But if it's for a 2 mark question, then you will do it like this. You will try to put a diagram, explain the things, and then work it out. Any questions about this at the moment? Okay, so having seen these two cases which are part of the syllabus, and you expect questions to come from this part of it, I'm going to talk about one more case, which is, they call this special cases. I'll call what I'm talking about as a very special case. Okay, which is when, what if the force is acting in the direction opposite to the displacement of an object? Okay, let us say that an object is moving. So it's actually moving, okay, and it's moving in this direction, right? And now a force is applied in this direction. Okay, you get the scene. It's like the train is speeding off the track, and Spider-Man or Superman or whoever it is applying a force in the opposite direction, obviously to try and stop the train from getting wrecked. So in this case now, let's see how do we apply the same work equation. So in other words, how much work is, I think there is a movie in which Spider-Man tries to do that, right? Every movie has somebody trying to stop a train. I mean, every superhero movie has at some point of time or the other. And I think there's one for Spider-Man. I don't remember one for Superman, but we just go with Spidey. So Spidey is applying a force in this direction. The train is going in this direction. Now the question is, how much work is Spidey doing on the train? And what does that even mean? Okay. So let's do the math. So first of all, write down the equation. W is equal to F times S times cos theta. Okay. Now we have to identify, first of all, what is theta. So theta in this case is again referring to our coordinate system. Now the other part, this part becomes important, and you'll see in a moment why. The displacement is in the positive x direction, but the force is being applied in the opposite direction. So what is the angle between these two things? You can reply in chat if you like. Slope situation, we will look at it a little bit later. If we understand these two extremes, then the slope situation also becomes clear. It will be the angle between the horizontal and the direction of application of force. Yeah, correct, 180 degrees. Okay, so theta is equal to 180 degrees. So now you just apply it into the formula, F times S times cos 180 degrees. And what is the value of cos 180 degrees? Anybody who has a scientific calculator can punch in the value and give me an answer. But Ishan did it just a little while back. Cos 180 is equal to 1, but more specifically, it is equal to -1, -1. Okay, so cos 0 is 1, cos 180 is -1. All right. Now that leaves us with another form of the equation, that is work is equal to minus Fs. Because it's -1, so I can remove the one part is taken care of, but the negative won't go anywhere. So that comes over there. So how do we interpret this? Is that we say that this work is a work done against the direction of motion. Okay, so the work done is negative work, which means that it is going to slow down this object. In the other case, when the force is being applied in the direction of displacement, the object is going to get accelerated. It's going to speed up. That's what happens, right? If you apply a force on an object, constant force, then the object will accelerate. But in this case, if you apply a force against the direction of motion, then the force is going to decelerate. And it's obvious, that is why Spidey does this. Spidey knows his physics and his maths quite well. Two examples to illustrate this principle that has been mentioned in your textbook. We can just discuss that quickly. One is work done by gravity and work done against gravity. We will be using this again when we are discussing gravitational potential energy, but I'll just briefly mention it over here. So when an object is allowed to drop under the influence of gravity, maybe I can have somebody holding it. Okay, when the object is dropped from a certain height and it falls down to the earth. Okay, sorry, the line is a bit crooked, but assume it's falling straight down. Is there a force that is acting on it? Yeah, there is a force. It's the force of gravity, and it's the weight of the object that creates the force. Okay, so this force is there. Is there a displacement? Yeah, there is a displacement. This height, God, I don't know why drawing vertical lines is so much more difficult than drawing horizontal lines. I've always noticed this. There is a certain height that it drops. So there is a force, there is a displacement. So therefore work definitely is being done. What remains to be seen is, what about theta? So what is the theta in this case? Use the coordinate system again. So negative y is in this direction. The displacement and the direction of application of the force is in the same direction. So when they are in the same direction, then theta is equal to, beg your pardon, theta is equal to 0 degrees. So therefore, when theta is equal to 0 degrees, cos theta is equal to 1. And therefore, work done is equal to F times S. I just told you that F is mg, the weight of the object, and the displacement is h. So this mgh pops out, and what that mgh, we will see that a little bit later. The opposite can be also taken into consideration. If you lift an object, okay, the object was here and you lifted it up, and this time now the displacement was in this direction. Okay, then was there a force applied? Yes, of course there was a force applied. You applied a force on the object in that direction. All right. Is there a displacement? Yeah, there is a displacement because you lifted it up. So now can we calculate what is the work done? Yes, you can calculate the work done because there is a force, there is a displacement, and you will see that the quantity of the work done obviously is exactly the same because the force and the displacement are in the same direction. So the same rule applies. Theta is equal to 0, cos theta is equal to 1. So work done is mgh. Okay, but in this case it is work done by gravity on the object, and in this case it is work done by u against gravity on this object. Okay, so that's just a sort of distinction between these two things. I hope that point is clear. Any questions you can ask me. Another interesting situation that occurs with regard to this is, let us take the example of the moon going around the sun. Just in a very rough and ready manner, think of the path of the moon as being circular. Okay, it's not really circular, it's elliptical, but for the time being, just consider as being circular. So now, just from our discussion of the circular motion, forces and circular motion and centripetal force and so on, you told me that instantaneously the velocity of the moon is in this direction. So therefore, you can also say the displacement is also in this direction. Okay, okay, yeah. But the force that is being applied on the moon, that is causing it to go in this circular path, is the centripetal force, and that centripetal force is acting in this direction. All right. So here is an interesting situation where there is a force acting, there is a direction of displacement instantaneously. Okay, so that is obviously not the direction of displacement. It's only if the centripetal force disappears that becomes the direction of movement of the object. Because of the centripetal force, the object of course keeps changing its direction of motion. Now over here, since the force and the displacement are at right angles to one another, this is a situation in which theta is equal to 90 degrees and cos theta therefore is equal to, or rather putting it directly, cos 90 degrees is equal to 0. And now the work done by the earth on the moon because of the gravitational attraction is going to be F dot S dot, I'm using the dot, you can put multiplication sign also, 0. So therefore the work done is equal to 0 Newton meter. Alright, so this is an interesting consequence. When an object is undergoing rotational motion or uniform circular motion, our textbook refers to as uniform circular motion, then the centripetal force does no work on the object. Okay, so that is an interesting consequence that comes out of our misunderstanding of work done. So with that, we come to kind of the end of this section, that is the special cases and some examples of the special cases. The kind of questions you can expect obviously in this is, it's a set piece question, it's a 1 mark question that we usually ask. Is work done by an object that is causing another object to undergo circular motion or uniform circular motion? The answer is no. For a 1 mark question, an object undergoing uniform circular motion has no work done on it because the displacement and the centripetal force are 90 degrees to each other. That's all you need to write, or you can just say no work is done. I think that it will be acceptable for a 1 mark question. Of course, if it's a 2 mark question, then you have to also give the reason.